Hello friends, welcome back to this series where we go through and explain the book on quantum mechanics by Steven Weinberg. We are now at chapter 2 on a particle in central potentials. In the last video, we have just finished our discussion of the hydrogen atom, which is essentially an electron bound by the Coulomb potential to a nucleus. That is just one example of a system described by such Hamiltonians. Notice that we have assumed that the nucleus is completely static, because none of its dynamical variables are present in this Hamiltonian. In this lecture, we shall show why this model still gives an adequate description of the bound states between the two particles, even though in reality the nucleus moves. All we have to do is to modify the electron mass, replacing it with a new value known as the reduced mass. This will be sufficient to take care of the effects on the bound states due to the motion of the nucleus, as we shall see. Let's now introduce the dynamical variables of the nucleus to build a more complete model. Recall that in previous discussions, the potential V only depends on the position of the electron with respect to the center of the potential. We now replace this by the relative position between the electron and the nucleus. That is, the nucleus now sits at the origin of V. The kinetic energy of the nucleus must also be included in the Hamiltonian. It makes sense to keep this relative position x as an independent dynamical variable, so as to preserve its relation with V, which we have been using up till now. The point is to find modifications to our previous model, instead of working with something completely different. We shall call x1 p1 and x2 p2 the old variables, because we are preparing to invent new ones. These are pairs of variables which describes the electron and nucleus that satisfy the usual canonical commutation relations. The commutators between variables of different particles are always assumed to be zero. Let's introduce a set of new variables that will include the relative position as a member. There should also be a momentum conjugate to this position. Together, they form a pair of relative variables. The derivation of this momentum will be postponed to later. Let's first look at the remaining variables. These are the center of mass variables. They are the center of mass position of the electron nucleus system and the associated total momentum. We expect the center of mass velocity to be constant, since the interaction forces between the two particles act in an equal and opposite way. xcm is therefore like a variable describing the collective motion of the two particles. We can get a clue about how to construct the center of mass position in terms of x1 and x2 by looking at the total momentum. P1 and P2 are related to their respective velocities by the usual relation, just the mass of the particle times its velocity. This relation can be extended to the two-particle system by requiring the momentum to be equal to a single mass times a single velocity, taking the mass capital M to be the total mass. The last equality should allow us to define xcm in terms of x1 and x2. This automatically implies the expected result of the center of mass velocity to be constant in time, since the total momentum is conserved due to the translational invariance of the Hamiltonian. Let's find xcm. This equation suggests that the expression within the yellow braces can be identified as the center of mass position. Now we will verify that xCm is actually the canonical conjugate of the total momentum. That is, we must show that they satisfy the canonical commutation relations. This is done by using the commutation relations of the 1-2 variables. Since the commutators between the variables of different particles are zero, we need to consider only the pairs corresponding to the same particle. Thus, the total momentum really is the variable conjugate to the center of mass position. We know that xCm commutes with the relative position x, since both are functions of just the positions x1 and x2, and all positions commute. But what about the total momentum? Let's find out. The indices labeling the components of the 3D vectors in the red boxes are hidden to keep things simple, but they are to be understood in this way, using particle 1 as example. And the results just cancel. Thus, we have shown that the relative position does in fact commute with the total momentum. Now we move on to the problem of finding the momentum conjugated to the relative position. Assume that this momentum is a linear combination of P1 and P2. This way, it automatically commutes with the total momentum. A and B are some constants that are to be determined. Let's calculate the commutator between xCm and this momentum. This commutator must be zero if it is to be an independent variable with respect to the center of mass variables. Notice that these two commutators are equal. This implies the following equation. The obvious solutions for A and B is this. They must necessarily be dimensionless, since these are coefficients in a linear combination of momenta. Let's substitute them back into P. This P will commute with the center of mass position. At this point, we have derived a set of relative variables, x and p, that are independent of the center of mass variables. That is, the two sets commute with each other. Since we have already shown that xCm and p total forms a conjugate pair, now we must do the same for x and p. The commutator between x and p can be calculated in a straightforward manner, using their definitions. Notice that the term within the yellow braces is just 1, since capital M is just the sum of M1 and M2. This is the reason why we have chosen it as the denominator in the first place when solving for A and B. Indeed, x and p form a conjugate pair. So we now have a new set of variables describing both the collective motion and the internal relative motion within an interacting two-particle system. Let's express the Hamiltonian in terms of these variables. Notice that we do not have to do anything with the potential V, since it is already a function of the relative position. We turn to the kinetic energies. Let's first examine the new momentum variables. We would like to express P1 and P2 in terms of these momenta to substitute into the kinetic energies. It will be convenient to write these two equations as a matrix equation. Then it's a simple matter to invert this equation using the inverse of the matrix. Thus we have the desired results. Let's substitute them back into the kinetic energies. Now we focus on this numerator. Both the squares can be expanded out. And we notice a cancellation. In the blue box, we have defined a new quantity, the reduced mass. This is the mass associated with the relative momentum P. Its name comes from the fact that it is even smaller than the smaller of the masses, which we take to be m1. Notice that the only place where a center of mass variable appears is the total momentum in the first kinetic energy. This means the center of mass undergoes free motion. The rest of the terms belong to the relative Hamiltonian, consisting entirely of relative coordinates. Of course, this means that the two Hamiltonians commute and are independent. Using this result, we can verify that P total is just the total mass times the center of mass velocity, which is a relation assumed in the beginning when we were deriving the center of mass position. But now we have to make sure that the time derivative in this equation is consistent with the time evolution generated by the Hamiltonian. That is, xcm has to satisfy the Heisenberg's equation of motion. Let's check. We can just use the center of mass Hamiltonian for this. This commutator is easily evaluated using the product rule for commutators derived in Lecture 2, and just gives the partial derivative of hcm with respect to P total, which is the total momentum divided by the total mass. This confirms the condition in the blue box. We now move on to the eigenstates of this Hamiltonian. Since hcm and h relative commute, they must share the same eigenstates. The part of disjoint state, which is the eigenstate of HCm, is just an eigenstate of the total momentum, as this part undergoes free motion, being driven by only its kinetic energy. The part that corresponds to the eigenstates of H relative is the kind of states we have been solving for the past few lectures. These are the internal bound states of the two-particle system. Therefore, we expect the associated energies to be discrete, hence denoted by En. The total energy is then simply the sum of the two independent parts, the kinetic energy of the center of mass plus the relative internal energy. Let's look at the wave functions of these states. To do this, we must take inner products with suitable position states. These are states with a definite center of mass position and relative position of one particle with respect to the other. To avoid confusion, we emphasize that the position operators are notated by bold font, in contrast to their eigenvalues in italics. The wave function of the joint energy state can be split into a product of functions, each dependent on only one set of independent variables. For the center of mass position, this is the familiar momentum eigenfunction, which carries the total momentum eigenvalue. While for the relative position, this is the internal energy eigenfunction, like the ones we have solved in the past few lectures. Let's see how the eigenvector equation of the relative Hamiltonian looks like in position space. Since the relative Hamiltonian depends only on the relative coordinates, the center of mass wave function just cancels on both sides of this equation. And we get this familiar energy eigenfunction equation that will give us the bound states of two particles interacting through the potential V. Except instead of the electron mass, we use the reduced mass. This is the result promised in the beginning of this lecture. The net effect of replacing the static center of the potential by a dynamical variable on the internal bound states is simply a modification of the electron mass. For describing the hydrogen atom in most applications, it is still okay to use the electron mass, since the mass of a nucleon is about 2000 times heavier than the electron. This makes the reduced mass roughly equals to the electron mass, which is quite intuitive, since we can expect a heavy particle to remain relatively static under the perturbation of a very light particle. However, the small shift in mass do have a measurable effect on the bound state's energies, as we can see from the formula in the yellow box, derived in lecture 14. Let m1 be the mass of the electron. For the regular hydrogen atom, the nucleus is just a proton. In this case, m2 is 1836 times the electron mass. This gives, for the proton-electron system, the following reduced mass. In the case of a different hydrogen isotope, the deuterium atom, the nucleus is a deuteron, which is one proton plus a neutron. This gives a slightly different reduced mass. This is enough to cause a measurable shift in the spectral lines of the two isotopes relative to each other, and allows astronomers to determine their relative abundance in the interstellar medium. This in turn tells us something about the conditions of the early universe when these isotopes are formed.